Hello everyone, I Sumon Mukhopadhyay. Our today's topic is error detection. So let's start the topic. So at first we have to know what is error in computer networks. Error is a condition when the receiver's information does not match the sender's information. During transmission, digital signals suffer from noise that can introduce error in the binary bits traveling from sender to receiver. That means a bit that means a 0 bit may change to 1 or a 1 bit may change to 0. When data is transmitted from one device to another device, the system does not guarantee whether the data received by the device is identical to the data transmitted by another device. An error is the situation when the message received at the receiver end is not identical to the message transmitted. And to detect this error is known as error detection process. In computer networks, error are basically of two types. Those are single bit error and burst error. Now let's see what is single bit error. A, si- a single bit error refers to a type of data transmission error that occurs when one bit, that is a single binary digit of a transmitted data unit is altered during transmission, resulting in an incorrect or corrupted data unit. Let's see the figure. In the figure, the sent data is 0, but the received data is changed to 1. The message which is sent is corrupted as single bit, that is 0 bit is changed to 1. This is known as single bit error. And the another type of error is burst error. The two or more bits are changed from 0 to 1 or from 1 to 0 is known as burst error. That is, multiple number of error present in the transmitted data is known as burst error. The burst error is determined from the first corrupted bit to the last corrupted bit. The duration of noise in burst error is more than the duration of noise in single bit error. Burst error are mostly likely to occur in serial data transmission, where single bit error does not occur in serial data transmission. Next slide is about error detection technique. The most popular error detection techniques are single priority check, two-dimensional priority check, checksum, and cyclic redundancy check. Now let's see the technique one by one. At first, single parity check. Single bit parity is a simple error detection method that involves adding an extra bit to the data transmission. It works as 1 is added to the block if it contains an odd number of ones, and zeros is added if it contains an even number of ones. In schema, this schema makes the total number of ones even. That is why it is called even parity check. In this technique, a redundant bit is also known as parity bit, which is appended at the end of the data unit so that the number of ones become even. If the number of ones become odd, then parity bit 1 is appended, and if the number of ones bit is even, then parity bit 0 is appended at the end of the data unit. Now at the receiving end, the parity bit is calculated from the received data bit and compared with the received parity bit. This technique generates the total number of ones even, so it is known as even parity bit. The next technique is two-dimensional parity check. Two-dimensional parity check bits are calculated for each row, which is equivalent to a simple parity check bit. Parity check bits are also calculated for all columns, then both are sent along with the data. At the receiving end, these are compared with the parity bits calculated on the received data. Performance can be improved by using two-dimensional parity check, which organize the data in the form of a table. Now discuss about the drawback of the 2D parity check. If two bits is in one data unit are corrupted and two bits exactly the same position in another data unit are also corrupted, then 2D parity check will not be able to detect the error. This technique also cannot be used to detect the 4-bit error or more in some cases. Now the next technique is checksum. Checksum error detection is a method which is used to identify error in the transmitted data. The process involves dividing the data into equally sized segments and using a ones complement to calculate the sum of this segment. The calculated sum is then sent along with the data to the receiver. At the receiver's end, the same process is repeated, and if all zeros are obtained in the sum, it means that the data is correct. In a checksum error detection technique, there are two parts, that is checksum generator and checksum checker. A checksum is generated at the sending side, which is known as checksum generator. It subdivides the data into equal segments of n bits each, and all these segments are divided together by using ones complement arithmetic. The sum is complemented and appended to the original data known as checksum field. The extended data is transmitted across the network. And in the checksum checker, a checksum is verified at the receiving side. The receiver subdivides the incoming data into equal segments of n bit each, and all these segments are added together, and then this sum is complemented. If the complement of the sum is 0, then the data is accepted, otherwise the data is rejected. Now see the diagram of checksum detection. Firstly, the data is divided into k segments of each of m bits. On the sender side, the segments are added using ones complement arithmetic and get the sum. The sum is complemented to the get the checksum. The checksum segment is sent along with the data segment. At the receiver's end, all received segments are added using ones complement arithmetic to get the sum. The sum is complemented. If the result is 0, the received data is accepted, otherwise it is discarded. Now the next technique is cyclic redundancy check or CRC. Unlike checksum schema, which is based on addition. CRC is based on binary division. In CRC, a sequence of redundant bits called cyclic redundancy check bits are appended to the end of the data until so that the resulting data unit become exactly divisible by the second. At the destination, the incoming data unit is divided by the same number. If at this step there is no reminder, the data unit is assumed to be correct and is therefore accepted. A reminder indicates that the data unit has been damaged in transit and therefore must be rejected. Let's understand the CRC technique by using diagram. A string of n zeros is appended to the data unit and this n number is less than the number of bits. Secondly, the new extended data is divided by the divisor, which is process is known as binary division. The reminder generated from the division is known as CRC reminder. Thirdly, the CRC reminder replaces the appended zeros at the end of the original data. The newly generated unit is sent to the receiver. The receiver receives the data from the sender followed by the CRC reminder. The receiver will treat this whole unit as the single unit and it is divided by the same divisor that was used to find the CRC reminder. If the resultant of the divisor is 0, which means that it has no error and the data is accepted. If the resultant of the division is not 0, which means that the data consists of an error. Therefore, the data is discarded. A CRC generator uses a modulo 2 division. Firstly, 3 zeros are appended at the end of the data as the length of the divisor is 4. And we know that the length of the string zeros to be appended is always 1 less than the length of the divisor. The functionality of the CRC checker is similar to the CRC generator. When the string 1010000 is received at the receiving end, the CRC checker performs the modulo 2 division. Sender will send the data 1010000 by adding 30 at the end, and the receivers received the data 101000011. The remainder is added to the original data, which is sent by the sender, and this is accepted by the receiver. Then receivers divide the received data by the same divisor 1001. If the remainder is 0, then the data is accepted. In this image, the remainder is 0, so the data is accepted in the receiver side. And in this way, the CRC technique is used to check the error. So our presentation is over. Thank you.